The Robotics Club at the University of Georgia recognizes the important relationship that agricultural workers have with their machines. However, we also wanted to focus on simplifying the design to better fit the needs of the agricultural worker so that he can better understand how the machine works. I'm Ethan McNally, the mechanical lead of the team. Aladdin Al-Khatib is the electrical lead of the team and is a computer systems engineering major. Riley Elwood is a software computer systems engineering major. Savelli is our public relations chair for the club and a computer science major. And Sammy is a computer systems engineering major. Dr. Li is our mentor and a professor in the School of Electrical and Computer Engineering at the University of Georgia.
The first major design choice we had to make was deciding if we wanted to collect data one row at a time, 2 rows at a time, or all 4 rows at once. Although collecting data from all 4 rows at once would have yielded a faster runtime, it would have required an expanding robot and a much more demanding design process, so we decided to collect only 2 rows at a time. Our approach was to fully design and test one side of the robot, then mirror the design and hardware functionality to the other side.
Research solutions. The mechanical team researched a couple different solutions to the problem and tested these out in the beginning. One was a conveyor belt seed deposit, which ensured that exactly one seed dropped every time. However, we found the exact timing to be very difficult, and the rotation of the belt was also a difficult task to accomplish. Therefore, we decided to go with an easier design. We also researched an overhead camera, which blocked out the light from above and had the same angle on every picture. However, this made the robot much more complex, and we did not want this for the agricultural worker.
Because majority of our team consisted of computer systems engineers, we decided to combine software and electronics under one team. Although machine learning and deep learning are paving the way for the future of robotics, they are not necessary for this type of project because the robot's task is narrow. It should be capable of completing a very specific task well. Another goal of ours was to minimize the amount of processing necessary for the task. We also originally wanted to use a color sensor, but the sensor itself was returning very inconsistent results. Ultimately, our solution to all these problems was to complete the task using image processing.
We decided to go with an all-direction drive system with 4 mechanism wheels driving almost flush to the ground. The mechanism wheels are attached to 4 AX12A Dynamixel motors housed in a custom-cut, low-cost acrylic chassis. We designed the chassis for easy accessibility to make adjustments and repairs as seen necessary. As for the seed deposit, the design is fully mechanical and 3D printed out of ABS. This design ensures that only one seed drops every time and that no excess seeds are dropped onto the field or in the cup. There is a reloading tube Two extension arms sit on either side of the robot. The design of the arms is simple, with easy adjustability. Different agricultural workers have different fields, therefore different earth materials and width between crops. This adjustability allows for us to change the length, the width, and the height of the arms to ensure that the arms are sturdy and at the length necessary for the environment. These arms are 3D printed out of ABS.
In order to solve the problems of plant detection and line following, we chose to use 6 infrared sensors. 4 of them were mounted onto the arms, making it 2 on each arm. The bottom one was for seed cup detection, while the top infrared sensor was for plant detection. If both went off, it would indicate that there was a plant there, but if only the bottom went off, then that would indicate a seed cup. The benefit of sensors on the arms would allow us to get really close without causing harm to the plants. For line following, we mounted 2 infrared sensors on the front. Electrical tape has a unique property which allows it to absorb infrared light, so we decided to take advantage of this with our infrared sensors. This would allow the robot to follow the line perfectly throughout the entire run. For image processing, our goal is to reduce the amount of information in the image. As you can see in the original image, we have the background of the white table, and we also have two surrounding green plants. To get rid of the surrounding green plants, we first crop the image. To get rid of the background, we then filter it. This reduces the information in the image to two things, black and yellow. Next, the image is run through a script that returns the two most dominant colors. The reason we need the top two is because the black background might be the most dominant, but the color we actually want is yellow. Another scenario may have the yellow as the most dominant and black as the second most dominant. So this script is designed to handle both cases. All we need to do to filter out the black is to add the two values together, and we always get a color yellow or green.
Construction. The first challenge that we faced during construction was, of course, working remotely. However, our team recognizes this crisis early on and managed to divide work that could be done remotely and in the lab to be as efficient as possible. The second is that we had a few team members graduate at the end of the year and left our mechanical team thin. The third is that because we did not have a lab, we had to send in our 3D prints to someone who could print them. And the fourth is that having to wire 6 motors to have the maximum amount of voltage in each turned out to be a challenge to us. Here's an example of us working remotely, as one team member set up the field in his apartment to test the robot. We made a few changes to the design throughout the process. The first is that we made the tolerances in the seed dropping mechanism larger so that it did not hit the ground. The second is that we redesigned thin areas of the acrylic base. And the third is that we drilled holes in the chassis for optimal wiring to the arms. Our total budget this year was $1,000, and we ended up spending only $567, so this was a big win for us.
We learned several things. Give tolerance. Assembly drawings are very important for understanding that tolerance as well. The third is that solid wiring is key to a good robot. The fourth is very much important, which is that low-cost items play major roles. And these include sensors, 3D printing filament, and acrylic. It's very important to invest in these so that you do not have to worry about investing in more later on. And this is the exploded view, so many different interchangeable parts and adjustable parts that we have. The changes that we made during testing, we actually switched our arms from the front to the back of the robot as we found that the sensors were in a better place and the camera was in a better place. And we also increased the distance from the seed deposit to the ground to ensure that no seeds fell out on their own, which we found during testing would sometimes get caught on part of the board and fall out. So once again, having that adjustability aspect in those arms made a huge difference for us. And this is how it came out. And it's exactly what we wanted, so we were very happy with the results. And we want to say thank you so much for holding this conference. We know that it's been a tough time for all of us, but I'm very glad, and I know that we are very glad to be able to send in this competition, whether it be virtual. So thank you for going through this.